In this problem, we are told that air expands through a turbine operating at steady state on an instrumented test stand. At its inlet, which is over here, P1 is equal to 160 pounds per square inch, and T1 is equal to 1,560 degrees R. At the exit over here, P2 is equal to 14.8 pounds per square inch. The mass flow rate exiting the turbine is m dot, and it is 10.5 pounds per second, and the power developed off this turbine is going to be 2,550 horsepower. Now, if we neglect heat transfer and kinetic and potential energy effects, we want to determine this exit temperature in degrees R. So first thing, let's define what our control volume is, and it's going to be this turbine, and we're going to have one inlet and one outlet. So when we start with our mass equation, our change in mass of my control volume over my change in time is the sum of my mass flow rates of my inlet minus the sum of my mass flow rates of my exits. I have one inlet and one outlet. So this is going to be equal to, and we're operating at steady state. So this is going to be equal to 0 is m, and we'll call this state 1. We'll call this state 2. So m1 minus m2. And that tells me that my mass flow rate of 1 is equal to my mass flow rate of 2. And we're told that they're equal to m, and they are 10.5 pounds per second. So now that I figured out my mass flow rate, I can use my energy equation. My energy equation is dE dt, and I'm going to write out the mostly full form. I am going to make a simplification right off the bat for a single flow, single inlet, single outlet control volume. So this is going to be equal to the work of the control volume, the heat transfer of the control volume minus the work of the control volume plus the mass flow rate of my enthalpy of my inlet minus the enthalpy of my outlet. And I called that 1 and 2 actually. So 1 minus H2 and plus the change in my velocity of my inlet minus the change in velocity of my outlet squared over 2, and then plus my change in potential of the inlet minus the change in potential of the outlet. Now, we can make some simplifications. Again, we have steady state, and because we have steady state, dE dt is going to go to 0. We were told that we can neglect heat transfer. Because we can neglect heat transfer, Q is going to go to 0. We can't neglect our work because we have a work output, but we can neglect our velocity because this is kinetic energy, and we can neglect our height change because this is our potential energy. So if we write our simplified equation, we're going to have 0 is equal to minus the work of my control volume plus my mass flow rate times H1 minus H2. I sort of messed that up, but that should be H2 at my exit. Okay, so now we need to realize that the substance we are working with is air. And when we're looking for our enthalpies, right, we have this from our problem statement. We have our mass flow rate from our problem statement, and we need to figure out what our enthalpies are. Now, the enthalpy for air is like if we deal with an ideal gas, and the enthalpy, H, is just going to be a function of temperature. Well, and remember, we need to use our absolute temperature. Now, in this problem, everything's already in absolute temperature, but we can figure out what H1 is. H1 is going to be our enthalpy of 1,560. So what we need to do is we need to go to table A22E. Well, in the book I use, which is the Fundamentals of Engineering Thermodynamics. So when we go to that table, we need to now look up 1,560. So this is what the table looks like. And how this table works is it's broken up sort of in half. So as we go down here, these are our temperatures. And we sort of go down and we get to 920. And then we have another column over here, which the temperatures continue. So then we go, all right, 920, 940, all the way to 1,560. And our enthalpy right there is 385.08. And our units are going to be, I didn't write these down, but BTU per pound. So let's bring that back. Over here, we'll have H1 is equal to 385.08 BTU per pound. And we now need to figure out what H2 is. However, we don't know the temperature H2, so we can actually solve our equation right here for H2. When we do that, let's say for H2, we'll have H2 is equal to, well, let's do it in 2 steps so I don't make a mistake. We'll have my mass flow rate times H2 minus H1. I move that to the other side of the equation, is equal to minus the work of my control volume. I'll have H2 is now equal to the work of my control volume over m dot plus H1. Okay, and let's give myself a little bit more room over here. H2 is going to be equal to minus 2,550 horsepower. Now, we have to convert horsepower to BTU, we have to convert horsepower to BTU. So the conversion we have is 1 horsepower over 2,545. This is in BTU per hour. And our flow rate is in pounds per second. So now we just need to convert hours to seconds. Okay, we're going to divide by our mass flow rate, which is 10.5 pounds per second. And then we just need to add in our enthalpy. So let's give myself, again, just a little bit more room. And add in this 385.08 BTU per pound. So we get H2 is equal to 213.4. And that is BTU per pound. Okay, we need to remember this. So now what we're going to do is we're going to take H2 and we're going to sort of do a reverse lookup in this chart. So rather than have a temperature and find H2, we're going to have H2 and we're going to find the temperature. So we go back to our table and we're going to start looking through H2. And let me write down what H2 is, just so remember H2 is equal to 213.4. So we're going to be looking through our H column and we're going to try to figure out where we get to 213.4. So we're going to have 213.4 somewhere over here. So let's actually get rid of this part of the table. And 213.4 occurs somewhere between 880 and 900. So what we're going to do is we're going to linearly interpolate. So we're interested in some temperature. So some temperature in between here. And we're going between 880 and 900. And we're using the enthalpy. So we know the enthalpy we're looking for is this 213.4. We're going at 880, our enthalpy is 211.35. And at 900, our enthalpy is 216.26. So now we can solve this equation for T. And we're going to get that T, get my calculator. So this is 20 divided by the difference in our enthalpies. Multiplied by the difference in this enthalpy. And then we add 880 to it. So we get this is 888.4. And we're in degrees R. So if we come back to our actual problem, we can write that our temperature at 2 is equal to 888.04 or 0.4 degrees R.